OK, so one more property that we mentioned when we talked about TLS design goals is forward secrecy. So let's spend some time thinking about whether this is provided by TLS. So as a reminder, what is forward secrecy? The scenario is somebody records an encrypted connection today. So they write down all of the encrypted values that you have sent across the channel today. And then sometime later, a week from now or a month from now, they hack into your computer and steal all of your secrets. If this attacker in the future is able to decrypt the messages that they previously recorded, we say the scheme does not have forward secrecy. That attacker in the future is able to come back and decrypt the things that they wrote down previously. However, if that attacker in the future is unable to decrypt previously recorded messages, even after stealing our secrets, then we say this scheme does provide forward secrecy because it stops the attacker in the future. So that's just a reminder of what the property is. So does TLS provide forward secrecy? It kind of depends on what type of TLS you're using. So remember, there were two different options for exchanging secrets. Let's see if I can find them. So one of them was the RSA approach to finding the pre-master secret. Now in this case, TLS actually doesn't provide forward secrecy. And to see why, consider an attacker who writes down all of these values. So they know the random numbers because they wrote them down, they're not encrypted. And they know this encrypted value because it was sent over the channel. And then they write down all of the encrypted messages after the handshake. That's all done today. Now we skip into the future. The attacker comes along and steals all of the server's secrets, including the server's private key. So if the attacker steals the server's private key, then they can come back to all the stuff that they wrote down. They can decrypt the pre-master secret using the stolen private key. Using the pre-master secret and the random numbers, they can generate the shared keys and then decrypt all of the messages. So if you choose the RSA option with TLS, you don't get forward secrecy. An attacker in the future could steal this private key and then use it to decrypt the pre-master secret, use that to generate the keys, use the keys to decrypt all of our messages. So RSA version of TLS fails the forward secrecy check. However, the Diffie-Hellman version does have forward secrecy. And the reason why is because Diffie-Hellman is ephemeral. Once you finish deriving the shared secret, G to the AB mod P, both the client and the server can delete A and B forever. There's no reason to keep A and B around forever. If they want to do a different handshake, they can use a different value of A and B in the future. So unlike the server's private key, which is something the server keeps forever, in RSA, the Diffie-Hellman version has secrets A and B, which can be discarded forever, never to be seen again. So even if the attacker writes all of these values down, if they fast forward to the future and compromise the server or the client, they don't know the value of A. It's been deleted. They don't know the value of B. It's also been deleted. All that they have is this stuff that they wrote down. And we already know that someone who sees G to the A mod P and G to the B mod P cannot derive the shared secret. So the Diffie-Hellman version does provide forward secrecy because A and B can be discarded after each exchange, whereas the server's private key cannot be discarded after every exchange. They have to use it every single time to match with the certificate. So that's the difference between the RSA and the Diffie-Hellman versions of TLS. If you use the Diffie-Hellman version of TLS, you do get forward secrecy, and the RSA version does not give you forward secrecy.